In this video, I will determine the irreducible representations of the vibrational modes of this molecule. In this molecule, xenon forms a double bond with the oxygen atom. The xenon atom also forms 4 single bonds with 4 fluorine atoms. This molecule belongs to the C4v point group. In the C4v point group, we have a C4 principal axis. We also have 4 symmetry planes. There are 2 sigma V symmetry planes and 2 sigma D symmetry planes. Each of the 2 sigma V's contains 4 atoms. For example, over here, 1, 2, 3, 4. These 4 atoms define 1 sigma V. Now let's look at 1, 2, 3, 4, including 2 other fluorine atoms, and xenon and oxygen. These 4 atoms define another sigma V. What about sigma D's? The 2 sigma D symmetry planes also contain the oxygen and the xenon atom. They bisect the 2 sigma V's. Now let's look at the C4v character table. There are 5 symmetry classes. In 1, 2, 3, in this 3 symmetry classes, each has 2 unique symmetry operations. So for example, here you can rotate the molecule about the principal axis 90 degrees or 270 degrees. And if you look at this symmetry class, because there are 2 sigma V symmetry planes, there are 2 different sigma V symmetry operations. Similarly, there are 2 different sigma D symmetry operations. So in total, we have 8 symmetry operations. Therefore, the order of the C4v point group is 8. Again, let's sum up the symmetry operations. 1, 2, 1, 2, 2. The total is 8. And now if we have 5 symmetry classes, there's got to be 5 irreducible representations. So we have 5 rows and 5 columns. Now let's look at this character table. Those numbers, if you see +1, that means symmetric. If you see -1, that means anti-symmetric. If you see 0, that means neither symmetric nor anti-symmetric. And now if you look at this one is kind of different from A1, A2, B1, B2. This is because over here we are looking at double degeneracy here. So over here, that means the translation along the X and Y directions are degenerate. The rotation about the X-axis and the Y-axis are doubly degenerate. So now let's look at the symmetry operations on this molecule. First, let's do the simplest identity symmetry operation. That means doing nothing. If you do nothing to this molecule, all 6 atoms remain in their original positions. That's why we put a 6 here under this E symmetry element. This E symmetry element means identity symmetry element. It means doing nothing. So we have 6 atoms remain in their original positions. Now let's look at this operation. So we have 2 C4 operations. We have C4-1 and C4-3. C4-1 means we rotate the molecule about the C4 principal axis 90 degrees. C4-3 means we rotate the molecule 90 degrees 3 times. So that's actually 270 degrees. But no matter you rotate the molecule 90 degrees or 270 degrees, only 2 atoms remain in their original position. So you put a 2 here. What about the C2 symmetry operation? Again, 2 atoms. The oxygen and xenon will remain in their original positions. What about sigma v's? There are two symmetry planes that are sigma v's. So one of them is this, that contains 4 atoms. So after this corresponding symmetry operation, these 4 atoms remain in their original positions. So you put 4 here. Sigma d's are different from sigma v's. So over here, sigma d's bisect, for example, this angle or this angle. Sigma d's bisect sigma v's. So if you do a symmetry operation with respect to a sigma d symmetry plane, well, these 2 atoms will switch their positions. These 2 fluorine atoms will also switch their positions. Only the oxygen atom and the xenon atom remain in their original positions. So we put a number 2 here. Well, now each atom may move in the x, y, or z direction. So now let's look at the characters for x and y. They are doubly degenerate. So I'm copying those characters from this row. All right. And then what about the translation along the z direction? I'm going to copy this row, okay, because I see this z here. So I'm going to copy this row here. Now I'm going to sum up x, y, and z. So over here, it's the sum of B12 and B13. And then I'm going to drag it from left to right to create all these 5 numbers. So these 5 numbers are simply the sums of these 5 numbers and these 5 numbers. We just need to know the characters of the x, y, and z translations of one atom. And then we need to do a multiplication. So this is for one atom. And over here, we know how many atoms remain in their original positions after a symmetry operation. So we have this row multiplied by this row correspondingly. So 6 times 3, we get 18. And then we drag it from left to right to fill all these 5 cells. Now, this will give you the sum of all characters that corresponding to the motion of these atoms. We need to subtract the translations and rotations from this row. So first, translations. Now we're talking about the translation of the entire molecule. And this is the same as this row. All right, so I just copy this number here and then drag it from left to right to automatically fill this 5 cells. Well, what about rotations? So we can have the rotation about the x and y axis right here. R sub x, R sub y, they are the rotations. So I copy this row here, 2, 0, negative 2, 0, 0. So they are here. And then what about the rotation about the z-axis? R sub z, 1, 1, 1, negative 1, negative 1. 1, 1, 1, negative 1, negative 1. All right, so we have translation of the molecule. We have the rotations of the molecule. Now over here, we have this 18 minus translation minus rotation. We have this 12 that's associated with the vibrations. And then I drag it from left to right to fill the 5 rows here. Now, these are the characters associated with all vibrations. We need to determine the irreducible representations, though. So we need to multiply this row with the characters in the A1 row, in the A2 row, in the B1 row, in the B2 row, and also in the E row. And then don't forget this. We have more than one symmetry operations in this class, and also in this class. So we need to multiply the corresponding numbers of symmetry operations as well. So let's click here. So this is B$19. This one. times B4 over here, and then times B$1. B$1, it's this one. All right, and then we enter, we drag it from left to right, and then we can drag it down here. Now we create all those numbers for this A1, A2, B1, B2, and E. Now we just need to sum up these 5 numbers and then divide the sum by the order of this character table. We'll get the number of A1 irreducible representations. So over here, it's the sum of these 5 numbers divided by the order of the C4v point group, which is 8. This $G$1 is right here. It's 8. And then we drag it down. Now we can see there are 3 vibrational modes that belong to the A1 symmetry species. 0, A2, 2B1, 1B2, and 3 doubly degenerate E.